Why isn't the set of rational numbers enough? Well, it all starts with a theorem that you're probably quite familiar with. This theorem was proved a while back by a people called the Pythagoreans. That's right, the Pythagorean Theorem. And it says in a right triangle with legs of lengths A and B and a hypotenuse of length C, C squared is equal to A squared plus B squared. So here we have a triangle with legs of lengths A and B and a hypotenuse of length C. So before we prove the Pythagorean theorem, we'll need a couple of basic facts from geometry that you might want to recall. First, the area of a square with side length S is S squared. And second, the area of a triangle with base B and height H is 1/2 B times H. So in the picture that we have here, the base has length B and the height has length A. So the area of this triangle is 1/2 B times A, or equivalently 1/2 A times B. Okay, so let's prove this theorem. There are many, many ways to prove the Pythagorean theorem. I'm going to give a simple geometrical proof. We'll start by drawing two squares, each of side length A plus B, by rearranging four copies of this triangle in two different ways. Okay, so here we have two squares. They both have the same side length, so both of these squares, these big squares, have the same area. And notice how we've rearranged the triangles to form these squares in two different ways. Now we can compute the areas of each of these squares by adding up the areas of all the figures making up each of the squares. So the area of the square on the left is 4 times 1/2 AB plus A squared plus B squared. To see this, note that each of these triangles has area 1/2 AB, and there are 4 of them. So we get 4 times 1/2 AB. The area of this small triangle is A squared, and the area of the bigger triangle here is B squared. This simplifies as 2AB plus A squared plus B squared, simply because 4 times 1/2 is 2. Similarly, the area of the square on the right is 4 times 1/2 AB plus C squared. The 4 times 1/2 AB comes from the 4 triangles, and C squared comes from the square in the middle. And we could simplify that to 2AB plus C squared, again because 4 times 1/2 is 2. Since the areas of both squares of side length A plus B are equal, we have that 2AB plus A squared plus B squared is equal to 2AB plus C squared. And now we can cancel 2AB from each side of this equation, and we get exactly what we're looking for. A squared plus B squared equals C squared. And that proves the Pythagorean theorem. Okay, here's a question. In a right triangle where both legs have length 1, what is the length of the hypotenuse? Here's a picture. Very simple picture that is a very real-world problem. By the Pythagorean theorem, C squared is equal to 1 squared plus 1 squared, which is 1 plus 1, which is 2. So the length of the hypotenuse is a number whose square is 2. Is there such a number? Well, we have a theorem here, theorem 5.6. The Pythagoreans proved that there does not exist a rational number A such that A squared is equal to 2. So let's look at an analysis of how we're going to prove this. We will prove this by assuming that there is a rational number a such that a squared is equal to 2, and arguing until we reach a contradiction. A first attempt at a proof would be to let a equal m over n be a rational number that satisfies m over n squared is equal to 2. Then m squared is equal to 2n squared. To see this, note that m squared over n squared is equal to m times m over n times n. That's just by the definition of what it means to square something. And by the definition of multiplication of rational numbers, that's equal to m over n times m over n, which again by the definition of squaring is m over n squared. Now 2 could be written as the rational number 2 over 1, and that implies that m squared over n squared is equal to 2 over 1. And by definition of equality of rational numbers, that gives us that m squared is equal to 2n squared, which is what we were just trying to show here. So we have m squared equal to 2n squared, showing that m squared is even, right? Because m squared is 2 times an integer. That's what it means for it to be even. We will then use this information to show that both m and n are even. This will require a little work, and we're going to use a theorem from the last lesson to prove this. Now, in our first attempt, the fact that m and n both turned out to be even did not produce a contradiction. However, we can modify the beginning of the argument to make this happen. Remember that every rational number has infinitely many representations. For example, 6 over 12 is the same rational number as 2 over 4 because 6 times 4 is equal to 12 times 2. Notice that in both representations, the numerator and denominator are even. However, they are both equivalent to 1/2, which has the property that the numerator is not even. We will use the fact that every rational number can be written in the form m over n, where at least one of m or n is not even. This is a fact that you may want to try to write out a proof for. Okay, so we're ready to prove this theorem that there does not exist a rational number a such that a squared is equal to 2. Assume, toward contradiction, that there is a rational number a such that a squared is equal to 2. Since a is a rational number, there are integers m and n, with n not 0, that's what the star means, not both even so that a is equal to m over n. Okay, the not both even part, this is something you should definitely check, that every rational number can be written in this way. So we have m squared over n squared is equal to m times m over n times n. That's just by the definition of what it means to square something, which is m over n times m over n by the definition of multiplication of rational numbers. And that's equal to a times a by direct substitution, which is a squared, again by the definition of what it means to square something. And that's equal to 2 by our assumption. And 2 could be written as 2 over 1. Thus, m squared times 1 is equal to n squared times 2. So m squared is equal to 2n squared. Therefore, m squared is even, because m squared is 2 times an integer. If m were odd, then by theorem 4.4, m squared equals m times m would be odd. Remember that theorem 4.4 says that the product of two odd integers is odd. So if m were odd, then m times m would be odd, but we know that m times m, which is m squared, is even. So m cannot be odd. So m is even. Since m is even, there is an integer k such that m is equal to 2k. That's the definition of being even. Replacing m by 2k in the equation, m squared equals 2n squared, gives us 2n squared equal to m squared, which is equal to the square of 2k. By definition of squaring, that's 2k times 2k. And we could use associativity of multiplication to rewrite this as 2 times k times 2k. So n squared is k times 2k, simply by canceling out a 2 on the left and right of the previous equation. And we could rewrite that as k times 2 times k, using the associativity of multiplication. And then using commutativity of multiplication, that's equal to 2k times k. And again, using associativity of multiplication, that's equal to 2 times k times k. So we see that n squared is even. And again, by theorem 4.4, n is even. Once again, theorem 4.4 says that the product of two odd integers is odd. So we have m even and n even, contrary to our assumption that m and n are not both even. Therefore, there is no rational number a such that a squared is equal to 2. So the big question is there an ordered field f with f containing the set of rational numbers and an element a in f such that a squared is equal to 2? We want this to happen, right? We have a geometry problem which shows that there is such a number. So the rational numbers just aren't cutting it here. We need some other number system where this number a, whose square is 2, exists. Luckily, the answer is yes. There is such an ordered field, and we call it R, the ordered field of real numbers. So next, we'll talk about what the property is that differentiates this field R from the field Q.